Great. Yeah, so thanks for the opportunity. And today I'll be presenting on, as what Jimmy mentioned, we want to build towards robotics foundation model that's able to do reasoning. And this is a work that just came out hot off the oven from Allen Institute of Artificial Intelligence. It's called MOMA. And I think I will sort of like start off with a narrative of what, is the motivation of doing MOMA. So I think we have really seen a huge advancement of robotics and in the past, decades, and robots has been able to do tremendous, great job for humans. But most of the time, these kind of robots are sort of in the industry setting, whereby it's most likely caged up and requires a huge amount of like pre-programming by human expert. So we are really missing that, the concept of a robot brain, because we want a robot brain that's able to sort of generalize to new environment, new behavior, new objects, and also, to do new tasks for us. And some of the recent work that shows the power of leveraging large foundation models to build such generalist robotic model has seen pretty much quite a lot of success. So examples from the Physical Intelligence Group or from like Toyota Research Institute, but if you look at all their demos, it's pretty moving towards one common goal, which is that we want models no longer to be able to do things for us in an industry setting or a factory that's caged up, but rather into our homes, whereby now the environment is more unstructured and which makes everything much harder. So how does like current state of foundation models for robotics really work? I think people have been adopting this paradigm of a vision language action model, whereby the model takes in an input and natural language instructions, and it outputs regardless whichever robot embodiment you use, outputs the 7-degree robot actions, and then you can use that to really control your robot in a closed loop manner. And the goal for me personally is that I want to have a robot that's able to, clean up the house after, as what you see from this scene, after a wild party, whereby there's so much, uncertainty in terms of, how do you actually go about reason about placing objects back into its original position. You need to be able to remember even like where is those position, that the object previously belongs to. So there's a lot more going behind just besides learning the action itself. And I think that comes back to the point where I would like to make from this talk, which is that reasoning is really important for building such robotics foundation model. And I guess there has been work that looks into using leveraging reasoning for building such VLA models. For example, embodied chain of thoughts, or the recent one from NVIDIA called ThinkCat. They're really good at leveraging this kind of reasoning capability from the language model itself. And we know that, people have a huge amount of success when it comes to using reasoning models in language model. And one of the most obvious example will be this chain of thought prompting from Google, which shows that, with just an intermediate process, you're able to get much better result than directly prompting it. But the question that I have is that, reasoning in language is ambiguous. Especially for motions in space. So we can't really use, the way we do reasoning for language or solving math question for the context of robotics, because robotics actually needs to be able to reason in space, and those reasoning need to be grounded. So with that, I'll present and share with everyone our work on MOMO, which is an action reasoning model, the first of its kind, that learns to reason in space. And the way that's really solved and enables MOMA is in the data itself. And one of the huge mission of Allen Institute of AI is that we focus on open sourcing everything from not only just the data, but from the training, the eval, and the entire pipeline that allows people to reproduce and validate the model. But the problem about robotics is that there isn't much, open source robotics data we could even start off with for pre-training. So like one of the most largest or well-known robotics data set that's out there is the OpenX embodiment data set. This is collected with collaboration with over 21 institutes and 34 research labs. It covers a wide range of different embodiments, robots doing tasks, in different lab settings. But the question is that, if we want to use this data to start off our pre-training, is the quality and the quantity good enough? So that's the first question that we have when we started this project. And then by actually having a deep dive into the OpenX embodiment data set, we realized that actually that might not be the case, because you have like robot trajectory that has really low quality in terms of visual observation. You have like, robot demonstrations where there's no language instructions or wrong language instruction, and you have no idea exactly what's the robot trying to do. And furthermore, you have, like in the droid dataset, you have demonstrations that looks like this, where the robot is just simply trying to grasp air. So these are not the good data that you want to actually use to train a large-scale foundation model. So the way we actually started is that we first look at the entire OpenX embodiment dataset, and we actually tell ourselves that we need much cleaner data. So we did a round of filtering. We filtered 1 million trajectory all the way down to only 190,000 trajectory, and focusing on three main data set within the OpenX embodiment dataset, which is the RT1 from Google, Bridge, and BCZ, which is also from Google. And beyond that, we need even more high quality data. So with that in mind, we actually scale up our data collection effort, whereby we collected additional 10K robot episodes. And these episodes are collected using a Franca robot in diverse household scenarios, doing tasks that actually is what humans will actually eventually want your robots to be able to do. And with that, we also further break down those like long real world horizon tasks into like shorter subtask sequence, whereby people could use that to train a model that's able to output a given long context task and output a subsequent subtask in order to achieve. And also, we also break them down into its individual atomic motions in the way that we collected the data. So it goes from like open, pick, flip, and place, and close the tray. And these are atomic skills that matters a lot in terms of manipulation. So we want to teach that into the data set, and it goes into like flipping the mark, even non-prehensile tasks, for example, closing the drawer. And with that, we're able to collect over 1 month many more high quality demonstrations per task. And in fact, we collected over 100 tasks of 100 demonstrations. Prior work looks like collecting more diverse data set, so there's less repeated data points, which actually makes it bad because in that context, diversity sort of hurts the training. And with all this data we collect, we are still far away from what large companies out there are trying to do. So with that, we have only about 200,000 robot episodes, whereas the Pi Zero model that's trained by physical intelligence uses about 1.2 million robot episodes. So coming back to the point, one of the huge takeaway of how people use reasoning in language model scaling is that you're able to get much more information given the same amount of data if you leverage the ability of reasoning. So we feel that we need to be able to leverage the ability of reasoning because we have much lesser data. So with that, we actually look at how can we curate reasoning data set for MOMA. So we developed MOMA to actually try to ground reasoning into pixel and further into 3D space. So the first thing we did was that we take those collected demonstrations. We use MOMO, which is AI2's in-house VLM model, to create these ground truth annotations of like points that points to the gripper. And if you put them together, you're able to get like a trajectory that tells you the plan that the robot should take. And this trajectory, if you try to visualize that on the image plane, you will actually get a line that's sketched towards the objective. And then using that, you're able to also condition it to predict action. And with that, we collected around like 30 million image trajectory pairs that comes out of these 200K robot trajectories. And beyond, just having a plan in mind, humans actually have a sense of depth. And this is something that is not often used in VLA training because it's all training on like 2D images. So how do we sort of incorporate this kind of implicit sense of depth? The way we do it is that we actually incorporated this thing called perception token in a way that we actually train a VQVAE model that's able to output these latent codebook tokens. And these tokens sort of represents the depth, the implicit depth of the image that you fed in. And with that, we are able to get these depth map tokens, which if you decode them, you actually get back a depth map in 3D. So putting all this together, we are able to curate what we call an action reasoning dataset, whereby you just take regular trajectories or robot demonstrations you collected, you are able to generate this kind of perception token, this kind of future depth trajectory token, which tries to reason about future actions, and then condition all of this on top onto an action prediction. And with that, we are able to train MOMO as a fully autoregressive model, and MOMO is able to basically sense the environment, it predicts those perception tokens, and if you decode those, you basically get a point cloud, and then condition on those perception tokens, you will actually sketch out the visual reasoning trace, and if you decode those, you will get lines that's being sketched on the 2D observation. And then on condition of all of these, MOMA will then learn to actually predict the action that is required to control the robot. And beyond that, we want to ensure that MOMA is also have strong visual reasoning capability. So we incorporated many image captioning, VQA, and even pointing dataset that's originally from the MOMO data mix. And this is what it looks like for our pre-training data mix. It covers from like general multimodal web data, going to auxiliary reasoning data for depth, which is to strengthen the model's capability to predict depth. Uh, Auxiliary line data that teaches the model to predict better lines. And this trajectory condition data is meant to help us to enable this ability of stability, which I'll mention a bit later. And the action reasoning data, which is what I mentioned just now, that really help us to optimize for less data but having much more information. And with that, we are come to our training paradigm. So similar to how VLA model is trained, we just go from VLA into like an action reasoning model by incorporating these kind of intermediate reasoning steps. We all start with MOMO, which is the VLM model, flagship VLM model from AI tool. We go through 3 stages of training: pre-training, mid-training, and post-training. And MOMA is able to do 2 things. MOMA is able to do reasoning in space, and at the end of the reasoning in space process, during inference time, you're able to get the action, the robot action that's required to control the robot. And MOMA is also steerable, which I'll talk a bit more later. So start with MOMO. So MOMO is a VLM model, which is trained in a way that it does vision language alignment. And you can think of it like if you try to ask MOMO to point to Mount Rainier, it can actually generate 2D coordinates in this kind of VLM training because of the data that it was trained on. And the problem is that if you use MOMO, just use MOMO alone and try to let it predict robot actions, for example, try to reach for this banana, you will not actually do anything sensible because all these multimodal language models are not trained to do vision language alignment yet. So with that in mind, the first thing we did was that, we started with this pre-training paradigm. And with this pre-training paradigm, we focus on purely autoregressive outputs in a way that the model will try to figure out, to first predict the depth, and then autoregressively condition the depth, predicts the trajectory, and then predicts the robot action. And for the pre-training stage, we use VQA dataset that I mentioned just now, and together with this 119,000 robot dataset that's formatted into this pre-training data mixture that I mentioned just now. And we train that essentially to do one thing in the first stage, which is to learn the world knowledge and action understanding. This is the most compute intensive portion of the training, whereby we need a strong base model. And we train this with like 256 H100 over a 24-hour span to get one checkpoint. And with the pre-training, which is a really good base model, and then we are able to embark on this mid-training. So the idea of the mid-training is to basically align the output representation in the way that you want your post-training to be, which now you include like multiple camera, different camera views, and the way you format the data is still going to be the same as the action reasoning data. But by doing so, you are able to, do one thing, which is to learn actions from very specific setting with high quality data from which is the MOMA dataset. And then once that is done, for any kind of downstream task that you would like to train MOMA specifically for, you can actually just collect like I think about 30 demonstrations of that downstream task and quickly deploy that downstream. And then we are able to do this with LoRa fine-tune, which requires much lesser GPU to actually train. And it's also much faster because we implemented action chunking during the post-training process. And with that, MOMA is able to do that 2 stage of inference, which I mentioned. This is the first stage of how the output looks like. And then towards the end, you will be able to extract the robot action required to actually perform the task. And the second, and the way you sort of also get a depth token is through this ground truth thing that we got from the depth anything. And then we will do the decoding from the VQVAE to actually obtain the perception token. And this is another example of what it looks like. And for the steerability, which is an interesting component as a result of our trajectory condition reasoning data, what it means is that because MOMA is able to output this visual trace, and you can sort of decode it to see what the policy is thinking. So that provides you with the additional interpretability of what MOMA is intending to do. And because you have that level of interpretability, you're able to now steer it. So for example, if you look at this simulation, the human is the blue color line, which tells it to actually go towards the cube. But halfway along the line, I change my mind. I start to that's where I draw, which is the blue cube. And then the yellow one is when, the model starts to reason about which action it's supposed to take. And then you are able to further steer the action forward. And with that, there's a few research questions that we really want to try to address with MOMA because as an action reasoning model, we really want to know how well does the pre-training do. So we use the simpler simulation benchmark to evaluate. We also want to know how effective is MOMO at in terms of adapting to novel new tasks, new domain, and new embodiment. So we use the liberal simulation benchmark and also real-world tests. And then we also want to know, how does the mid-training help to improve MOMA as a generalist model. And lastly, we also want to figure out, how MOMA generalize beyond its training distribution and how steerable is MOMA as compared to other ways of steering this kind of policy. So the first one is simpler. So simpler is a simulation benchmark that measures the distribution of the pre-training data that was collected. So with that, we are able to show that MOMA achieve a really strong base model performance in this simulation, much higher than many of those like state-of-the-art models. For example, Groot, OpenVLA, RT2 from Google. And we show that, even when fine-tuned on MOMA, you are able to get much higher performance, and the generalization does not drop during the variation aggregation evaluation. And on top of that, we also do post-training evaluation on Libra. Libra is a simulation benchmark that is used for VLA post-training evaluation. And we compare mainly to autoregressive model that doesn't use action expert head. And we found that MOMA actually outperforms all of these autoregressive models. That's mainly reasoning-based models significantly, especially for like long horizon tasks for Libra alone. And for post-training further, we also show that MOMA is able to generalize, to different embodiments from both single manipulators to bi-manual manipulators and increase performance significantly. And we also show that for mid-training wise, because you do the mid-training process, now any of the downstream tasks that you try to fine-tune on, you naturally get a 5 to 10% performance boost consistently. And we are also able to show that MOMA is able to generalize across different variations from like language variation, spatial variation, different distractors, new object. And for steerability, we want to test whether is MOMA steerable, not just through evaluating it on like, can we have humans to inject this kind of visual trace through an iPad to sort of sketch a line on the iPad. We also want to compare how well does that perform with like language-based steering, which is that now humans use natural language to try to steer the robot policy. And we found that actually with the visual reasoning trace, the model is much more robust and receptive to that steerability. And as a result, we are able to steer the policy to achieve the node level, to achieve the downstream task that we actually hope to achieve. And this is one example. So for example, MOMA is the yellow line is what the model predicts, and halfway as the yellow line changes its plan, humans come in. So for example, the last frame, the yellow line goes to the last coaster, and then I come in and sketch a line, and then we are able to steer that policy towards the top right coaster. So yeah, with that, I've come to the end, and I'm open to take any questions. Yeah.